This is a continuation of our discussion of thermochemistry and thermodynamics. We have finished chapter 10, which focused on calorimetry and enthalpy, heat of reaction. And in chapter 10, we talked about the first law of thermodynamics, which says that energy can neither be created nor destroyed. And in this chapter, we are going to focus on entropy, which is an important part of thermodynamics, and it explains to us why certain processes are spontaneous and why others do not occur. I want to set the tone for this lecture by asking this question. We know that the first law of thermodynamics tells us that the total energy of the universe is conserved, that energy is neither created nor destroyed. If that's the case, then why are we worried so much about running out of energy? Why are we told to conserve energy, that there's a limited supply? What is that all about? It turns out that although the total amount of energy is constant in our universe, the energy is continuously becoming less and less useful to us. So there are several different ways the second law of thermodynamics can be stated, but a simple way to understand, I think, is that as energy is transferred or transformed, so as energy is delivered from power plants to our home, and then converted from electrical energy to light energy or heat, etc., every manipulation of energy results in a dispersal of that energy, or you can think of it as a dilution of that energy. And that dispersal or dilution of energy is called entropy. And that is continuously happening in our world. The energy that's available to us is becoming less and less useful to us. And that is the heart and soul of the second law of thermodynamics. And it is the second law which says the entropy of the universe is always increasing. In other words, energy is always getting more and more dispersed. That explains a lot of the natural phenomena that we see. For example, the second law, or entropy, explains why energy always flows from a higher temperature to a lower temperature. Think about it, right? Think about a high temperature. That's a concentrated form of energy. It's a useful form of energy, right? And that as we know, though, that as we heat something up, it's going to immediately start transferring that energy as heat to something that's cooler. And by doing so, the energy becomes more dispersed, more spread out, more dilute, and less useful to us. But by doing so, entropy is increasing, and that's the second law of thermodynamics. So we could say the same thing, similar thing about energy flowing from a high pressure to a low pressure. If you know anything about weather patterns, high pressure pushes into low pressure areas, okay? And again, you think that is concentrated energy. High pressure can do a lot of work for us. And by spreading out, it's less useful, but it's also increasing entropy. Same thing as higher voltage to lower voltage. All of these processes are natural and spontaneous. Okay, they happen on their own in our world. Okay, so this is relatively trivial, but I'm very annoyed here because I have no less than 5 times tried to change the font of that. I don't know how it ended up purple, and apparently I have forgotten to save it each time. All right, so let's look at equations that represent the second law of thermodynamics. Okay, in other words, that the total entropy of the universe is constantly increasing. So one way to put that in formula is like this. Okay, total entropy is always increasing. But what I want to remind you, we've talked a lot in this unit on thermodynamics, thermochemistry, about system and surroundings. So you need to be very careful as we proceed talking about entropy, that although the entropy of the total universe must be increasing, that is not necessarily true about the individual entropy changes in a system we are studying, okay? So it is possible for a spontaneous chemical reaction, for example, to have decreasing entropy, okay? But what that would mean for that to be a spontaneous process, if the entropy of our system is going down, which is not naturally favorable, that would mean that the entropy of the surroundings is going up even more than going down in our system. And therefore, the total entropy change for the universe would be increasing, as is required by the second law. And just a minor little note here. We learned previously in chapter 10 that enthalpy, to be favorable, is less than zero. In other words, has a negative charge. Okay, that our world prefers when the enthalpy of a system goes lower. It's lower in energy, right? So just to keep sign straight in your head, entropy is the opposite. Okay, so delta S for a favorable process is greater than zero and therefore has a positive sign. So as we move through this chapter, just keep in mind that if we're talking about spontaneous, that means natural processes that occur on their own, they're favorable, that you want to be looking for delta S values that are positive and delta H values that are negative. All right, so now let's wrap our head around entropy from a tangible point of view. Like if you're looking at a chemical reaction, how do you know if entropy is increasing or decreasing? Well, the best way that scientists who are really studying it explain it is from a statistical point of view, but I'm going to try to make that a little bit more real. I'm going to be referring to freedom of motion for you, okay? So let me just highlight it. Something has higher entropy, right? The more freedom of motion it has. So the more the different ways that a system can move, the more freedom it has to move around, the higher its entropy will be. All right, so maybe just make a note of this. Just experience has told me that's the easiest way for students to be able to evaluate systems as far as entropy. All right. So I told you that most scientists that are seriously studying this approach it from a statistical point of view, and they talk about microstates, which you might see a bit about. I know it's in your book also. And basically, the more microstates a system has, and you can think of that as energy states. So if something's at a very high energy level, you can distribute that energy in more ways, okay? In other words, it's going to have more microstates than something that's at a lower energy level. There are fewer ways you can distribute the energy of a system if the overall energy is lower, okay? So, all right, so think of a microstate as an arrangement of the energy available to a system. And again, the more microstates, okay, or the more different ways you can arrange the energy or distribute it in a system, the higher the entropy will be. So to give you kind of a tangible idea of freedom of motion or microstates, okay, these are all the different ways molecules can move, right? They can bend, they can stretch in different ways, they can rotate, they can translation fly across the room. Those all represent combinations of those. All the different combinations of those movement represents microstates that account for the energy available to a system. So the more the system can move around, the more different ways it can move around, the higher the entropy. Now, although we're not going to be doing calculations, I do want you to be familiar with the equation that's often used when scientists study entropy from a statistical point of view. So S, of course, is entropy. And don't worry, right, that's just a constant, Boltzmann constant, but don't worry about that. All I want you to see is that entropy is proportional to the natural log of W. W is the number of microstates. So the bottom line is, as the number of microstates increases, entropy increases. Okay? So what are some specific conditions that will alter entropy? Well, some of the more common ones you're going to run into are if temperature increases, the entropy of the system increases. Makes more sense, right? I love this diagram that shows that. As you increase the temperature of something, you've given it more energy, more thermal energy, and so the microstates available to distribute that energy among the system increase. Okay, remember, higher number of microstates, higher entropy. Entropy also increases when volume increases. So it may be easier for you to think of, if you have a larger volume, there's more freedom of motion, right? So again, that allows more microstates, more configurations to distribute the energy with a higher volume. Entropy increases when you have more individual particles. So let's think of something like diatomic chlorine, right? Let's call that entropy, we'll just call it X. Now, what if I did something to break apart the diatomic chlorine so that I had 2 chlorine atoms instead of 1 chlorine molecule? The entropy of that would be X plus something, okay? The entropy would increase because the freedom of motion of 2 individual particles is greater than the freedom of motion of 1 combined. So imagine that you're holding hands with somebody and you're told to run as fast as you can. You're probably not going to be as successful or have as many options when you're holding hands with somebody as you would if you did not have to hold hands, right? So freedom of motion increases entropy. Now this may seem a bit counterintuitive. We're going to just look at one compound and talk about how the entropy, how the structure of that one compound can affect entropy. First of all, the more linear, the less crowded, the higher the entropy. Again, think about freedom of motion. So let's compare these two structures. These have exactly the same chemical formula. They have 8 carbons and 18 hydrogens, both of these, all right? The bottom one is much more bulky and crowded and confined than the top one. So I think it's pretty easy to imagine that the top one, octane, has higher freedom of motion and therefore higher entropy. The bottom one is not going to have, it's going to have constrained motion because they're going to start bumping into each other, okay? So again, the top one you can think of as having more microstates. The second thing that I want to mention, we can also see a similar effect when we're comparing carbon complexes. So diamonds are simply a bunch of carbon atoms. Each black sphere represents a carbon tightly bound to one another in a 3-dimensional network. Graphite, what is in our pencil lead, is also just a bunch of carbon atoms, but it occurs in layers. So you'll have a layer of carbons and then very closely set next to it another layer of carbons. And this layering is why graphite works so well as a pencil. It's kind of the layers of graphite shutting off as we write with our pencil. But in any case, I think you can probably imagine that in the graphite form, there is more freedom of motion. Okay, in other words, which translates into and more freedom of motion means there's more ways to disperse the energy in the system, or more microstates, and therefore twice the entropy that carbons arranged in diamond structure has. And finally, in general, an increase in mass of the substance usually means increased modes of motion, and therefore increase in entropy. So for that, let's compare, let's say, methanol to ethanol. Ethanol has a higher entropy because if you think of all the different, well, it has more atoms to do more movement, right? So it has more modes of motion, more microstates, and higher entropy. So what are we going to do with entropy? We have learned about enthalpy, heat content, and now we've learned about entropy, the level of dispersion of energy. We're going to put those two terms together, enthalpy and entropy, and it will allow us to predict whether a process will occur spontaneously or not. Spontaneously means that something will occur on its own without outside intervention, okay, in nature. Spontaneously, it's important to understand that spontaneously says nothing about speed. So you can have spontaneous processes that are extremely slow, but they're still happening on their own without outside intervention. So in later chapters, we will learn about the things that affect the speed of a process. We call that kinetics, okay? But that's not what we're doing in this chapter. What determines the speed is, you can kind of think of it as how high of a hill reactants have to climb to get to the other side. And just like you climbing a mountain, right? The steeper it is or higher it is, the longer it's going to take you to get to the other side. So, but for now, talking about thermodynamics, all we're doing is talking about the difference in energy between reactants and products. And now we know that that energy is combined of enthalpy and entropy, both. So just to kind of emphasize the fact that something being spontaneous has nothing to do with speed, the formation of rust is actually a spontaneous process. You leave something outside in nature and you don't have to do anything special. It's made of metal, it's gonna rust. And anything that is spontaneous in the forward reaction will be non-spontaneous. In other words, will not occur in the reverse direction on its own. All right, so why do spontaneous reactions occur? They occur because overall, the energy overall, so remember we're looking both at enthalpy and entropy, okay? The energy overall is decreasing, and that's what determines whether a process will occur spontaneously or not. Now, it turns out that if a process is exothermic, in other words, if the change in enthalpy is less than zero, is negative, right? That most of the time, if something is exothermic, it'll be spontaneous, but not all of the time. That's the role of entropy here. Okay, so if you wouldn't have learned about entropy, you might look at an exothermic process and say, oh, that's going to be spontaneous. Not necessarily, right? There are actually some endothermic processes, things that actually absorb heat in order to occur, that occur on their own spontaneously, and it's because of a favorable change in entropy. So let's talk about some of these processes that seem unfavorable with respect to enthalpy, but favorable with respect to entropy. I want you to think about melting ice. If you take an ice cube out of the freezer and you just put it on the counter, it's going to melt spontaneously, right? As long as the temperature of the surroundings is greater than the melting point of ice, right, which is 0 degrees Celsius, it's going to melt spontaneously. But let's try to figure out why. Because melting is always an endothermic process, right? In order for something to melt, it's got to absorb heat from the surroundings. That is endothermic. That means that delta H has a positive sign for melting, and that's not favorable in nature, right? In order for change in enthalpy to be favorable, In nature, it's got to have a negative sign. It's got to go to lower energy. So why then does ice melt spontaneously if the enthalpy change is unfavorable? It's all because of entropy. Okay? So I want you to think on a molecular level what's happening if you go from ice, which is the molecules are very tightly packed to one another, as is any solid, and then as it melts and becomes liquid, the intermolecular forces are loosened. The molecules have more freedom of motion in a liquid. And so what does that mean with entropy? That means that change in entropy is increasing. It's positive. It's very favorable. And in the case of melting ice at room temperature, which is spontaneous, that occurs because the favorableness, I think I just made up a word, of entropy is more important than the unfavorableness of enthalpy. Another very similar example would be evaporation, right? So when it rains, eventually the rain is going to evaporate spontaneously, right? And some comes out, or even if you spill water on your counter, it's eventually going to evaporate and spontaneously. And so again, anytime you go from a liquid to a gas, so anytime you vaporize, evaporate or boil a substance, it is endothermic, right? It requires input of heat. And so again, delta H would be positive, which is unfavorable. So why do things evaporate spontaneously if enthalpy is unfavorable? Same thing again. Compare the molecular view of a liquid versus a solid. Which one has greater freedom of motion? In other words, greater entropy. It is the gas, of course, right? Gas has greater freedom of motion. That means the entropy of a gas is higher than the entropy of a liquid. And that's why it happens spontaneously. Entropy in this case is more important than the enthalpy. That won't always be the case, but in this process it is. One final example. We know that if we take solid salt, table salt, and we stir it into water, as long as we don't put in too much, or even put it in water and let it sit for a while, it's going to dissolve, okay, spontaneously. We know that salt dissolves spontaneously on its own without intervention in water, okay? That is a spontaneous process. And again, it's primarily due to an increase in entropy. Again, you can look at the freedom of motion of a solid material versus the freedom of motion of the components of the solid material once it's dissolved in water. There's much more freedom of motion when a solid is dissolved, and therefore the entropy goes up, and that explains why sodium chloride is spontaneously soluble. So here's another trend in entropy that we see. The entropy of a gas is always higher than the entropy of a liquid, which is always higher than the entropy of a solid. There are a couple of different ways to estimate the overall entropy change of a process. One of the ways, and we use this as one of the ways for calculating the enthalpy change in a process too. So entropy change of a reaction is equal to the sum of the absolute entropies of all the products minus the sum of absolute entropies of all the reactants. So I think you probably, hopefully, remember that we had a similar reaction for change in enthalpy of a reaction, and it was the sum of enthalpy of formation for products minus sum of enthalpy of formation for reactants. So what's similar here, it's always products minus reactants. Okay, products first. And again, always put brackets around the entropies that you're adding together so that you will remember to distribute this negative sign. One key difference in using this equation for entropy is that the entropy for an element in its standard state is not zero as it was for entropy of formation. So if I had something like bromine gas, well, actually bromine's a liquid in its natural state. So if I had bromine, its entropy of formation, standard entropy of formation would be zero. And remember, I said that's something real important to remember. It turns out the entropy of any element, even if it's in its standard state, is never zero. And so, and basically that's a reflection of there's always some degree of motion in any component. And so entropy, that's actually a third law of thermodynamics, which we'll talk about. But entropy never goes to zero. Absolute entropy never goes to zero. The third law of thermodynamics says unless you have a crystalline solid at 0 Kelvin. And I'll finish this lecture of entropy by working a sample problem for you. Calculate the standard entropy change in vial for the given reaction. Now, just as with entropy of formation, you must be given a table of values of entropy. I do want to point out something now, and I'll point it out repeatedly, that the units given for entropy are usually in terms of joules. The units given for entropy of formation are typically kilojoules. Okay, so just be really careful of that, because eventually we're going to be adding changes in entropy to changes in enthalpy, and you got to make sure those units match. All right, so here are the entropies for all of this substance. Again, notice that elements in their standard state do not. They have a value for entropy, so don't assume they're zero. So let's let the problem worked out. So the entropy change for this chemical reaction is the sum of entropy of the products. So we have 4 carbon dioxide for a product. The other product is 6 water. Be careful, because the entropy value for a water liquid is going to be different than for a water gaseous or solid. So be real careful you get the right state of matter. So, and remember to multiply the coefficients by the value of entropy, minus the sum of the entropies of all the reactants. Be very careful to have brackets here so that you remember to distribute this negative sign. We have 2 ethane molecules and 7 oxygen. All right, so when you combine all those values together, you get that the overall entropy change for that reaction is minus 680.2 joules per mole Kelvin. Now, what does that mean? Okay, that's a negative change in entropy. What does that mean? Well, first of all, that means the entropy is decreasing, which means the freedom of motion is decreasing, and that is not favorable in nature. Remember I said a few slides ago that you want a delta S that's positive if you want it to be favorable. So entropy is unfavorable. That's not to say that this reaction won't occur spontaneously, because remember we have got to look at enthalpy also. And as a matter of fact, this is a combustion reaction, okay, which we know combustion reactions occur spontaneous. And if we were to calculate the change in enthalpy for this reaction, we would get a very large negative value, which is favorable. So in the next slide, you're going to see how we use both the change in entropy and the change in enthalpy in a reaction. Sometimes they have a tug of war with each other to determine whether the overall process is favorable and spontaneous. And that's it for entropy.